Hello, welcome to this presentation of the RoSE project, Learning in Routing Games for Sustainable Electromobility. My name is Henrik Sandberg and I'm a professor in Decision and Control Systems at KTH. This project is in collaboration with Assistant Professor Hampei Sasahara, who is a former postdoc at KTH, Professor Saurabh Amin at MIT, and Professors George Dan and Gyoso Ginofalvi at KTH. This project is funded by C3AI, Digital Transformation Institute, and Digital Futures jointly. The project has been going on for about a year now, a little bit more, and the main goal is to look at traffic routing for commercial logistic operators and to basically help them improve, make their traffic routing more sustainable by accounting for various factors, such as electromobility and operational costs. Our technical approaches are threefold. First of all, we employ simulations to estimate travel delays and costs using electrified transportation versus using combustion engine vehicle transportation. We look at optimization, basically looking at various traffic routes, how to find them, and also to try to investigate trade-offs between total costs and fairness, etc. Finally, we use game theory and learning, and that we used in order to model the interaction between different commercial operators when they compete for shared resources, namely the traffic, the transportation network, the roads, and also the charging infrastructure. Let us first talk a little bit about the simulation part of the project. So here to the right, you see a traffic network in the southern Sweden, and this is basically the background. We have imported data from about 1 million transport routes from heavy freight trucks, and we have split it into 5 kilometers road network segments like this. And the colors here illustrate how much these road segments are used in this past traffic, and also how much energy is needed in order to sustain this type of traffic flows. So this energy needs to come either from gas engines or combustion engines, fuel for those, or from the energy, electrical energy to supply electrical vehicles. So that basically gives us some sort of input to our routing to see how much resources are needed. And you can look at this data by using this address down here to the left. Looking forward, we use these simulations now to assess future routes and different scenarios, where we again would like to look at the transportation costs now for new routes, and also try to estimate the queuing times, basically in this charging infrastructure, how much time we need to charge the vehicles needed on the different routes, and also look at emissions, etc. So this leads into a digital twin that we will develop. Currently, these type of simulations are being deployed in the C3AI DTI cloud, which will be something that we will further talk about later. Moving on to the other activities in the project, we have the optimization part and also the game part. And here you see a simplified model we use for those studies. You can think about this network here to the right, where we have an origin and a destination. And for the sake of argument, you can think about the origin as Stockholm and the destination as Gothenburg. And on this route now, these routes, you have a number of competing logistical operators, each having fleets of ICEVs, electric internal combustion engine vehicles, and electric vehicles. And they basically need to transport goods across these routes. Each operator needs to ship N amounts of commodity, and they need to choose how much they should ship on ICEVs and how much they need to ship on EVs. And in the case of EVs, we also look at the time it takes to charge the vehicle on the way. So each electrical vehicle route has a charging infrastructure available, and that is something that we take into account. So each operator needs to basically choose a vector, so that how much traffic goes, how much goods goes across the ICVs, how much goes across the different EV routes, so that you basically deliver the required amount of goods. And this becomes what we call, in technical terms, an n-player atomic routing game. To make it a game, we also need a cost function, and currently we use a simplified cost function. One models the delay, the cost of delay on the shared electrical vehicle routes, and the other one models the pollution costs. So there is some sort of tax assumed here on the amount of pollutions that you let out when you use ICE vehicles. So for each commercial operator, you have this vector of shipments, and there's a cost function that's split into terms like this, R+1 terms, where the first one accounts for the pollution cost. So there's a factor alpha, which is the rate of pollution cost per unit of goods transported. And then we have a cost function like this, a convex function that is assigned to each EV route. So if the total traffic on a certain EV route is below a threshold chi, we assume that the charging infrastructure can support that without incurring any extra delays. And then there's no delay costs. Whereas if the traffic exceeds this limit, we assume that the traffic will build up. There will be a queue building up at the charging station, and that will cause delay in the deliveries, and that will cause costs for the companies. So these two costs need to be balanced by these different companies. Since they're competing now for the same resources, we model it as a game, and we call this the green routing game. And to find a solution, we employ the concept of Nash equilibria, which basically means that we try to find allocations of traffic so that no player has any reason to deviate from that solution. And that is, again, that's what a Nash equilibrium is. In our paper, we're just going to present later this year at IEEE Conference on Decision and Control. We have proven that these Nash equilibria always exist, but they're not necessarily unique, which is not so uncommon. But we have shown also that they are actually essentially unique if the operators offers the same service costs, so to say. So if they're more or less identical in terms of their cost structure, then these Nash equilibria are more or less the same. And by essentially unique, what we mean by that is basically that the total costs to the players are the same, even though the Nash equilibria may be different. And here are two different Nash equilibria where we have basically shown a scenario where you can reassign the flows a little bit, but the total cost is still the same. So in this sense, such equilibria are essentially the same. And that's why we say essentially unique. So here is an example of how the analysis can be used. Let's consider a simple case. We have two operators. In this case, we assume that one of them needs to ship 100 units of goods and the other 150. And we assume they have identical cost structure, which means then that there's essentially unique Nash equilibrium in this case. If we now let them play the game and compute the Nash equilibria, here you see the solution for player one. So basically it means that you should put most of the traffic on the internal combustion engine vehicles, some of the goods on EVs on route 1, and a little bit less on EVs on route 2. And now we compare this to what is called a social optimum. So this is if there is a centralized social planner who tries to minimize the total costs of society and then computes what will be the optimum. So it's not a game. And in this case, you see the outcome is that the player one should put all of the goods on the combustion engine vehicle. And that may seem a little bit odd. And the reason for this is that in this scenario, we put the costs alpha on the tax on the pollution is very low. So that makes sense then. If you play the game, so if the players myopically play the game, then they get this solution. But what we get then is the so-called price of anarchy, which is equal to 1.63. So this means that the total cost of the Nash equilibrium is 63% higher than the social planner. So this is not a situation we like. But we do notice that if we increase the taxes on the pollution, in this case with a factor of 50, so a dramatic increase, and then we compute a solution, then you can see that the social optimum and the Nash equilibrium, they're still a little bit different in terms of the allocation across the routes, but the total cost to society is more or less the same. So this scenario means that when the players play the game, and do whatever looks most beneficial to them, that also, in terms of total cost to society, agrees with what a social planner would have done. So this is a better situation, and this is something we would like to investigate more in the future. So in summary, we have investigated the green routing game. We are looking at multiple competing logistical operators that shares roads and charging infrastructure. So there's a trade-off between a larger delay then on the charging locations if you put a lot of EV traffic on them, versus a higher pollution cost if you put it more put more goods on the ICEVs. We have investigated the concept of Nash equilibria when they exist. And we are also looking into how to evaluate costs and other externalities from large-scale simulations. Going forward, we are continuing with looking into this parallel simulations of the detailed simulator that we are developing. And we're also looking in repeated games where the operators are learning over time and how they will converge to a desirable social optimum. So basically, how do we set up the cost structure so that this game will lead to a socially desirable solution concept? And by that, I would like to thank you for listening.